really happy to be with you. So the content of the presentation will be about the molecular modeling and molecular spectroscopy at the National Research Center. And the National Research Center is actually like CNR. It's for all Egypt. It's not for some regional people or something like this. So for many groups are working with me, are working in several universities in Egypt. And then I make an introduction about molecular modeling, what I mean with molecular modeling and so on. And we have two specific examples. The first is gas sensing device, and we got Egyptian patent in this work, and I'm going to make a presentation about our work. How can we combine modeling with experimental work, and then for the remediation of heavy metals from the aquatic environment. This work was really involved with Anna and Paula, and I was carrying part of this work here, and then conclusion and outlook. So the first is who I am, and what is the National Research Center, what's Ain Shams University, and our group, and etc. So my name is Medhat, and my family name is Ibrahim. Ibrahim is much easier to you than Medhat. I'm a professor of molecular modeling and spectroscopy working in the National Research Center. I'm a member of the National Committee of Physics. It's a committee in the Academy of Scientific Research and Technology also. I'm a member of the Web of Nuclear Research, the Academy. This is my citation data according to Scopus. I have several publications. This is my H index and citation and so on. I got some prizes in the national scale. The last one was a state prize in technological science. It was just 1 month ago. I got the golden medal in Egypt, and this during the prize was the minister and the head of the Academy of Scientific Research and Technology. I'm proud that I'm working in this field. So we are African. We're coming from Egypt, of course, and Egypt is in the northeast of Africa. We just crossed the Mediterranean to the old civilization, the Roman civilization. One time, Egypt and Italy was in one unity. You know the history better than me. And then this is a map of Egypt. Actually, we are coming from two close to each other parts. So the first one in Giza. Giza and Cairo are the greater Cairo in Egypt and separated by the River Nile. Here is located the National Research Center close to the River Nile. I work and I live in this area, and Dr. Hanan Hayes, Professor Hayes, is working at Ain Shams University, just 10 kilometers away from each other. Okay, if we're going to speak about Ain Shams University, it's the first university in the universe. As far as I know, it started with On University, 5,000 years old. On University was very famous in ancient Egypt, because you know that we have a very ancient civilization, and also we are here in Europe in the land of civilization. As far as we know that one of the teachers is called Imhotep, and Imhotep was a very famous Egyptian architect. It was 2,700 years before Christ, and he designed the first largest structure of stone, known in history as Zoser State Pyramid. It's in Saqqara. So the first engineer in Egypt was really working at Ain Shams University, which has the old name On University. One of the papers told us that one of the rectors of the university was the founder of the first dynasty. And we have so many special things in the ancient Egyptian time. But in the modern time, states the Ain Shams University, it's Arabic word for the word On or the word Heliopolis. So it was 1950, and now it's 18 faculties, 3 postgraduate institutes, 200,000 students. It's a very, very large amount of students. I know it's not the case in Europe. And 20,000 postgraduate students, 5 international scholars, 5,000, and 20,000 staff working in Ain Shams University. This is the university where Professor Hanan Hayes, by the way, she's my wife, okay? She's working in this university, and this is the main campus of the Ain Shams University. They have 7 campuses like this, located in Cairo. Again, I'm working in the National Research Center, which is similar to CNR here in Italy. It's started with the name National Research Center in 1956, but 20 years earlier was named by the King Fuad I. But the name National Research Center is started in 1956. It's the largest multidisciplinary research center in the Middle East region. So, in the starting, there was 4 divisions. A division in our research center, like faculty in the university. Each division is separated to some departments. We have 14 departments in the beginning. My physics research division, spectroscopy department, was part of this 14 constitutes the National Research Center. And now we have 14 divisions with 108 departments. So the manpower of the National Research Center is not so high like Ain Shams University, but it's 7,600. But National Research Center is the largest in our area. So, I'm belonging to a small group working in spectroscopy department, working in physics division, working in the National Research Center. We have some kind of service. We do it for public or for our colleagues with some money. We have some equipment and some computational facilities. This is our group, not only from National Research Center, but some of them are working outside the research center from different universities and outside Cairo. So, why I am here and how can I start here? In fact, 8 years ago, I was involved in the Egyptian-Italian collaboration. After the Egyptian Revolution, it was in the Italian Parliament. I made presentation there 8 years ago, and I started to know Giuseppina Capriotti. This was the starting point. 1 year later, I was invited by Giuseppina and Franco Borselli in Egypt because of Italian Days in Aswan. Then I come back to Rome. We make a workshop, and this workshop, I know this gentleman, Marco Ferretti, and then each event you start to know one Italian colleague. Then I go to Turin. It was also Egyptian-Italian meeting, and then we start to stack 1, stack 2. Giuseppina Capriotti is now in Cairo. She's half Egyptian, by the way, and I start to collaborate with her. Then we invite our Italian colleagues in some events in Cairo for spectroscopy, a different application of spectroscopy and so on. Okay, eventually we have 3 collaborations. Started with Giuseppina, of course. It was under the umbrella of Academy of Scientific Research and Technology and CNR. It's photogrammetry, of course. We work with Andrea Angelini and so many other colleagues, and of course Giuseppina, technology for the Egyptian cultural heritage. And we start from our side some modeling for soil at and around archaeological sites. And we make experimental FTIR, then we make some kind of modelings, and I will present few about this project. Then we start another collaboration with Marco Ferretti, and I'm lucky to work with those great people. We start joint instrumental investigation of museum collections as a means of enhancing cultural heritage and strengthening interdisciplinary collaboration. It was really very important that we start to make collaboration in this sense. We work with X-ray fluorescence, FTIR, and some molecular modeling, and finally, we have a collaboration as a spectroscopic analysis for natural microsphere for maximizing its application in the remediation of inorganic pollutants with Paula and Annie. So, starting from here again, what we will do is to study, for example, the molecular structure of soil at and around archaeological sites. We were working in Kopet al-Hawa in Aswan, and then we found some interesting results that there is organometallic interaction. We have some ligand found experimentally already in the soil, and then we found that this could be a transport for sodium chloride, for salinity, and for organic pollution from the surface to the groundwater. We study by molecular modeling what is happening to the thermochemical structure of the soil at this area. We found that salinity will be increased and thermal stability will be decreased, which is dangerous for the future of these important sites. This was completely theoretical based on FTIR experimental work. We have published something with Giuseppina, some environmental challenge in the aquatic environment observed in Nile. Then we make some kind of instrumental analysis for the Coptic icons. And Coptic icons, we have a problem in Egypt that Coptic icons is fragile. We start with Marco Ferretti. We bring some samples from broken icons in Egypt and from churches, and we study with attenuated total reflection infrared. It's a particle technique. And then we study another work with X-ray fluorescence by Marco Ferretti. We make by molecular modeling a combination between this elemental and organic structure. And we found that, as you know, that the Coptic icons, or even the icons, consists of several layers, and then we make the analysis for different layers with different techniques. The most interesting that we have two layers in the Coptic icons. One of them coming from egg yolk. It's amino acid, and this amino acid is going to interacting with some metal oxide and the metal hydroxide. As a result of this interaction, it could be some humidity, so water molecules is going to go. So this is structured like this. This is a water molecule, and this is a water molecule, and so on. Total dipole moment is increased. According to that, the chemical reactivity is also increased. This makes some cracks because of these chemical reactions, and these cracks is affecting the making fragility of the Coptic icons. We have published this work 2 years ago with Marco Ferretti, as I told you, and that's why I'm here. So we have 3 collaborative projects with CNR between my group in Egypt and different groups here in Italy. What we are doing with molecular modeling, this is the second step. I'm going to make few words about molecular modeling. So what do you mean by modeling? In fact, modeling is a kind of physical or logical representation for a given system. You have a system and you would like to understand the behavior of this system. You make a model to understand what's going on. This model is logical or physical. What's simulation? Simulation is the creation of the model. So if you are going to describe the system with a modeling, you have to make a simulation to know what's going on in this system. I'm speaking about molecules, so that the system here is molecular modeling. It's a modeling for a molecular system to understand what is the molecular interaction is about. The question is why we are doing modeling and simulation. In some sense, if you are going to describe the effect of pollution on the woman, pregnant woman, basically it's not allowed that you are studying the effect of some pollution on living organisms, even not living human. If you are going to describe what is the effect of nuclear explosion, you will not going to make experimental explosion to study what's going on. In some sense, you have to do simulation when the experimental work is limited or unavailable or ethically forbidden. So if we are going to describe the aquatic environment, for example, modeling will be very effective to describe some interaction in the aquatic environment. The basic of molecular modeling here depends on Schrödinger wave equation. But Schrödinger wave equation, as we studied in the university, is second-order equation describing the wave function for the total energy of electron circulating around the nucleus. To move to a molecule to describe the Schrödinger wave of a molecule, we make assumption that there is interaction between two electrons and 2 orbitals. They make a non-fly zone, and then we have some exchange correlation. For example, if you are going to describe the water molecule, it's chemically, it's interaction between electron from hydrogen and the other electron from oxygen. This S state electron, this is P state. So simply, it's 2 interaction between sp electrons. That's all. If we make a correlation for the interaction between these electrons here, this will be the total energy of the molecular system. Understanding the energy is the first key to understand the system as a whole. And then the model in this sense is approximation to solve Schrödinger wave equation. I will go through the theoretical basis, how to make a model. This is the main point in our work. To make a model molecule, you have to have a target. So why you need to make a model? This is your target. And then to build the model molecule, and then to choose the theoretical method. But in order to make a model molecule, you have to be, this model must be simple, short, and descriptive. Let's go to this, for example, the structure of humic acid in the environment. If we describe that humic acid is hydrocarbon chains, aliphatic and aromatic, could be from different origins. If it undergoes degradation, some bacteria will go through this humic acid structure. I'm going to make a model for how can I describe the interaction of this humic acid with heavy metals, for example. So we can see that we have some kind of aromatic and aliphatic. We can simplify the model as benzoic acid and say acetic acid. So both are describing the model molecules for humic acid. It is not important to have a very big chain, just the interaction is depending on the coordination, the type of coordination itself. So we have to choose three kinds of levels: semi-empirical or ab initio or density function theory, depends on the type of atoms you have in your structure. And then you put in a computer, you choose the most, is a method, and you put some data, and then you make data analysis. This is the most rigid part of the presentation. Then application, I know that all of you are working in the field of application. So gas sensing device for the detection of gas and volatile organic compound. What I'm going to do here is to describe what is the gas sensor. And to work with the gas sensor, you have two aspects. First one is you develop a material, and in this material, if this is a surface, you have the gases interact with the surface, physical properties of the surface is changed. And this surface is a part of a circuit, and it undergoes a signal. You get the signal, increase the signal, and then you have some kind of alarm. For example, if you work with a volatile organic compound or gases, and this stem is interacting with the gas, giving a signal, that's the process of gas sensing. So some people working in the development of the material, and other people working in the design of this circuit to increase the signals coming from the surface itself. Actually, we are working in the implementation of gas sensors materials, or nanocomposite working as a gas sensor. First, we have to consult the so-called nanomaterials, and we have developed our own technique for chemical vapor deposition. This is a homemade. We got Egyptian patent in this system as well. We increase the reaction zone. We have here some kind of hydrocarbon gas, and argon is carrying this gas. We make temperature gradient here, so we make some kind of reconstructing the gas itself, such cell assembly or something like this. We have hydrocarbons. By treating them with temperature, they become to be formed as carbon nanotube, multi-wall carbon nanotube with some kind of purification. We got a very, very simple way to produce carbon nanotube. And then we make lyophilization for carbon nanotube to increase the surface area. This is the same quantity of the multi-wall carbon nanotube. After lyophilization, it becomes a little bit with a very, very high surface area with this technique. And then what we are doing is to calculate if we are going to describe the interaction between some gases and the metal oxide, for example, we have to study something called the selectivity. If I have many gases, I have to be selective for a certain gas. So selectivity could be done by means of this theoretical method through the energy of interaction. I'm going to interact with A structure, so it costs 3 electron volts. If I'm going to interact with B structure, it's for 4 electron volts, so this is the most probable than this. That's why we have different schemes like this. This is a single wall carbon nanotube decorated with metal oxide. Actually, metal oxide itself could work as a gas sensor, but it needs some kind of activation. If you put the carbon nanomaterials with metal oxide, semiconductor, it could work, but in room temperature, so we save energy. We have tried different schemes. Each scheme of this in one of our published paper, and then we study even the electrostatic potential to know where is the active site, where is the metal could go, or where the volatile organic compound can go, and then we can go to our colleague working in experimental work. They are with our group, for example. We said if you are going to describe zinc oxide decorated over carbon nanotube, you have to make some kind of activation for the surface, and there was a source of zinc for this, and make interaction finally to put the zinc oxide as a nanocomposite in the surface of carbon nanotube, and you got interdigitated gold electrode, and this is finally our sensor. In some sense, we would like to increase the selectivity to consult the two surfaces. We make it like sandwich-like. We got the graphene or graphene oxide, and then we got metal oxide this side and that side. So we increase some kind of surface area, which is increase the possibility for the interaction, like the paper we have published here. I leave some papers in this folder if someone would like to have a look. So again, it's molecular modeling is the first step for the choice of the selectivity, choice of the combination between which metal oxide. You have different metal oxide. You have a multi-wall carbon nanotube, single wall carbon nanotube, graphene oxide, and so on. You have different choice, which is very expensive. Then if you work with theoretical methods, you have different schemes. Just choose a little schemes to be treated experimentally. So you save money, and the disposal of these chemicals will be eliminated or reduced. In this sense, you can dedicate this class of computational work to be very effective in the work of volatile organic compound or detection of harmful gases, not only in the laboratories but also in industrial areas. We have designed the chamber to know the detection limit, because detection limit is very important. In this design, we bought the sensor here. This is the actual chamber, and we can make a flow for a gas and calculate the concentration. And you get also Egyptian patent in this chamber to calculate the detection limit for the gases which is exposed to the surface of the material. We have some applications in the gas sensor, and that's all in this point. Okay. The most important point which I will present now is the modified natural microsphere for the remediation of lead from wastewater. Okay, first we have to assign what is our problem, and then why we are working in this salvation of this problem. According to the construction of many dams in Egypt and reservoirs, we have the annual peak discharge was reduced from 8,000 cubic meter per second. It's now 2,550 cubic meter per second, because of we control the level of water in the Nile. And then the sedimentation is nearly disappeared because of we have different dams. So the industrial activities along the river Nile is increased. We have two problems. Water flow rate is decreased and the industrial activity is increased. And we throw the industrial waste to the Nile without adequate treatment. Like we show here, it's not only water pollution, it's also air pollution across the river Nile, because most of the Egyptians are living in the Nile Valley. So our civilization, our life, our daily life is concentrated at and around the river Nile. What we do is to study the molecular structure of the sediment in the aquatic environment of the river Nile. If you look to this, we start from Aswan to Delta Dam in Cairo, you will find that the molecular structure is almost the same. So what is the fate of pollution? What is the organometallic interaction? What's going on in the aquatic environment of the river Nile? Of course, we try to do some tricks that we make a grain size distribution, for example, here. And the assignment is something traditional. But our work is to study, for example, what if we have a metal and this metal is going to be hydrated in water. This metal is thrown to the aquatic environment of the river Nile, and the metal is going to hydrate it and this hydration is going that the metal is coordinated with the ligand. For example, could be a hydrocarbon, aliphatic or aromatic, such in different schemes like this. For example, this is a monovalent metal like sodium. Sodium is going to dehydrated, coordinated with two water molecules, and then going to carboxyl group of the benzoic acid, for example. And as I said before, benzoic acid is a molecule for humic acid. We have already humic acid. I got some soil or some sediment and make extraction from humic acid and measure this extraction with infrared, CSR, NMR, and I'm quite sure that I have already humic acid in the aquatic environment. So that when I propose a model for humic acid, I'm sure that I have humic acid. What I can see here is I could measure theoretically the carboxyl and metal carboxylate, so that if I go back, I have here, for example, seem to be that this class of bands are a metal carboxylate. Seem to be that it was carboxyl acid of humic acid was stated like that, and then as a result of continuous interaction between this carboxyl group and this metal, it undergoes interaction and then it's located in a new position. In some sense, you could have it like this. Still, you have the carboxyl group, and this is the metal carboxylate. This is seems to be that the ligand is going to take the metal away, and then a metal carboxylate is located in other band structure. And the problem is this process is going back. So the metal is transported by this organometallic interaction from a location to another across the river Nile. But if the vice process took place, the metal could be ionic, and then in this case could be going to the fish or going to the other aquatic life. So the problem of organometallic interaction could happen like this for divalent metals or monovalent alkalis like this, and with different schemes. I make a comparison between theoretical structures and actually experimental structure. I found that all of these schemes could be happened in the aquatic environment. The problem is this is responsible for a transport of pollution. Organometallic interaction is going to be like this. The pH is the change of water, it's sedimented, so that a pollution is localized from state to another by this class of interaction. On the other hand, it could be as well another interaction from the surface to the groundwater. So could be this class of transport could be responsible for the increasing pollutants in groundwater in Egypt, or even increasing salinity. In this sense, I have already with Josephina make a model that a transport of salinity is going from the surface to the groundwater, and this is increasing salinity around archaeological sites. I got some samples from the depths, and I go to neutron activation analysis in Russia. It was 4 years later than this project, just did 1 year ago. I found that the level of sodium is increased with depth. So the model is verified. This class of increasing sodium in this depth means that if a sodium is going to interact with this ligand, with leaching or the water going down, it could leave the sodium alone, which is something like transporting sodium from the surface to the near groundwater. It's at 18 meters or something like this. I got some core samples and I showed that this model could be having like this. And we have already published something in spectrochemical about this spectroscopic analysis of soil samples outside Nile Delta of Egypt. Then we published some papers about the aquatic environment of the river Nile, experimentally and theoretically speaking about this interaction happening in the aquatic environment and in the Delta region, where we are all living in this area in Egypt. Now, this is a problem. So we have increasing amount of heavy metals in our aquatic environment, in our groundwater. What we are doing to overcome this problem? Okay. So let's go back to nature. This is our answer. If you would like to propose if we're going to propose a surface like this, I would like to have a big surface. This surface is enough for adsorption of metals, and I propose some kind of carboxylic group, for example, or functional group, and this functional group could act for complexation. So you offer a surface, but this surface is natural, it's already found in the environment, and this natural surface could act as absorptive state, as a complex state to remediate heavy metals. This is our strategy to work like this. And then what we are doing here, we got aquatic plant. This aquatic plant is Ecornia water hyacinth. This is growing in Egypt, not only in Egypt, in tropical and subtropical regions of the world. And then I got this plant as dry matter. I got natural polymer. I make this implementation in ionic cross-linker. Just to drop water hyacinth, dry matter, with a polymer, together with ionic cross-linker, it becomes like a sphere. So the surface sphere will be unlimited, because the sphere is going everywhere. And then if we insert some kind of acetic acid, functional group could be acetate, and then you will verify this. In this sense, it works like this. I got water hyacinth, and then I got some polymer, let's say ketosane, which is a polysaccharide. It's also natural. So we are speaking about natural structure, could be found in the environment. I start with 5% of dry water hyacinth, together with 95% of ketosane, and ending with 70% of water hyacinth and 30% of the polymer itself. As you see, this is the removal of lead within half an hour. Okay, so within half an hour you could remediate something like 8%. Let's make a comparison between this microsphere results and the results for activated carbon, nanosilica, nanozinc oxide, and nanotitanium dioxide, which is very expensive. It's comparable results. So let's go back. We have here a surface. This is the surface of a sphere, and in this sphere you are building structure. Seem to be that natural polymer with natural plant together as a sphere, and you bought cross-linker, and with a cross-linker you bought the functional groups. Functional group have a strong hydrogen bonding. This is our thinking, that we, if you have a metal in the environment going to be complexed, it could be complexed like this, or could be absorbed in the surface. It works. We got already Egyptian patents, and then we start to modify our work with powder. Okay. How to modify this work? This is a question. Okay. We start like this. This is water hyacinth. Let's dry like this. Okay. 105 overnight, and then put with some kind of sodium alginate, for example. Why sodium alginate? We say that ketosane is expensive, so we have another polysaccharide, which is sodium alginate, could be calcium alginate as well, and then we make the same experiment here. This, by the way, this is we done last year, I guess. Last year here in CNR. Okay, this is the sphere. We put it in water, and this is the surface of the microsphere with the electron microscope. Oh, we got some kind of published work in this sense, and then we would like to make this process cost effective, because it was very expensive to work with ketosane. We got ketosane from Germany. It's very, very expensive. We have to do it with less expensive materials. In order to scale up our work, there are some problems to be solved, such as to make a substitution. So we have to consult quantum mechanics again. What we can do to have the same results of ketosane, and we have it with a cheaper price. Then cost-effective production, we have to use solar energy, for example. This is our work here with the lovely group of Dr. Paula and Dr. Anna. Yes, they study their work in the effect of bacteria. I can, of course, talk on this because I'm a physicist. we have published a paper about the effectiveness of a new Greek technology for metal water, and we decide that so quantum mechanics, if you have cellulose-like material or protein-like material, so a material has amino acid, strong hydrogen bonding, you could have a sphere. We start this with Dr. Paula here. We have some Italian orange, and we got this, and then this was a microsphere from orange skin. I don't know the name in English. It works. Why? Because if you go back to this model, you have to put first, you got the polysaccharide, and then polysaccharide in water, and then you get this dry matter is going to make something like a composite. This composite, it's a class of, you are building this material together with a cross-linker. It works like this. And then we start to think, what we are doing is we have a mixture of cellulose and lignin. This is our model. Of course, plus some metal oxide. We have the water hyacinths, we have the carrots, we have the residue of the tea, we have here the orange, and so on. We could make analysis with X-ray fluorescence, with electron microscope, with infrared, and you know, the Laplace structure, the elemental analysis, the metal oxides, and then we design our surface like this. So for starting with simulating water hyacinths, it's not only cellulose and lignin, it's cellulose and lignin plus ketosane. This is our first structure, plus metal oxide. Surface morphology is going like this. You have different morphologies, and this morphologies offers the surface as a good absorbed state to be the metal to be absorbed. And then if we make a substitution, we do the sodium alginate is going instead of the ketosane, it has a carboxyl group. In this sense, this carboxyl group has strong hydrogen bonding, which is coordinating heavy metals. It could work like this. So we have in the existence of water molecules, this is our simulation for the structure, and by this way we bought sodium alginate instead of ketosane. Sodium alginate is much less expensive than ketosane. So it works like this. Sodium alginate have electrostatic potential. It has many active sites. So the interaction is not only through the carboxyl group. It could be through the surface of the sodium alginate. That's what quantum mechanics said. And in this sense, here the orange is doing the same. So sodium alginate, cellulose, ketosane almost have the same active sites from the point of view of quantum mechanics. And then let's make the sphere and go to the sphere. It looks like this. This is the surface morphology, and the question: what is the fate of heavy metals in this sphere, and what is the rate of removal? So we got sodium alginate and got some treatment of deeping experiment with, I do this in Egypt, with carboxyl group. Seems to be that if you bought the sodium alginate for a long time, for a short time, it got some kind of saturation with acetic acid. We got free carboxyl group, and then we increased the number of hydrogen bonding. In this sense, we bought this functional group on the surface itself. Okay, what we are doing now is to use a solar heating system to make drying for the plant, and then we can start like this. We have also generating some electricity that the work will be cost effective and could be also green. In this sense, we are applying for a patent in this work. And here is, if you are going to see, this is sodium alginate and this is different concentration of water hyacinths. You see that the structure is almost the same. So we succeed to put sodium alginate or the plant inside each other. So the structure seems to be that it's a part of the plant itself. So we build this structure as a big sphere, able to remediate heavy metals from the viewpoint of experimental FTIR. This is starting from 30% up to 70% of water hyacinths with this sodium alginate. And we have different materials. as I told you, we could choose every cellulose-like material, protein-like structure could act, and we could do the microsphere with them like this. It's almost the same, and here the cross-linked sodium arginate with water hyacinth. We can see that could be on the surface. So it works in this sense like adsorbed state. Okay. By infrared, we could prove that the existence of complexation. And let's speak about what is the rate of removal. For example, we have here the removal of cadmium with different composite samples. And this is a control sample. This is shoot part of the water hyacinth plant, the root, the total plant, carrots plant, orange, and tea. Even the residue of tea could be produced in the form of microsphere, and even it has a rate of removal. It's not so high, but it's not bad also. By the way, it works within 2 hours, not half an hour like our starting results. We have also here the cadmium. Okay, the removal of cadmium this is the rate of removal in 2 hours. Okay, this is for 2 concentration of cadmium. One is high concentration, other is low concentration. And this is the results of lead. Okay, the removal was in orange is 87% could be removed in 2 hours, which is a big amount to be removed. If we speak about 2 stages, we can eliminate lead from the wastewater with this kind of microsphere. So it's very natural that why we are choosing this aquatic plant, why we are choosing this agriculture residue. In Egypt, we have a big problem that water hyacinth is consuming water. It's growing abundantly, so we pay some money to get rid of this plant. In Egypt, we pay something like 800 million pounds each year that this through the river Nile. If we put it in dry matter and then put it as a microsphere, so we can gain some money from producing this aquatic plant into microsphere used for in the remediation of heavy metals. Okay. Then again, this done by Paula to see the existence of metals here in the surface of the microsphere. We got the microsphere and seem to be that it's adsorbed on the surface. In this sense, if we make some kind of regeneration, we can get rid of this metal and use the sphere several times. We use it for up to 6 times in Egypt. It could work more and more in this sense. So it's not really a conclusion. Let's open again what we can do in future. For example, we now working in an instrument to make not a mass production, semi-pilot microsphere. We can produce something like 2 kilograms in 1 hour because we work only with the tip, and now we can produce some amount of this microsphere to be scaling up our work. And then we have a handmade electrospinning technique. We can produce instead of a sphere, we can do it like fiber. Okay, I know that there is an institute here have already developed this more modern technique than this, but it's handmade. Also, we have something a little bit different. We think that if you are going to make substitution, you make sodium alginate instead of ketosane. What about the cross-linker? Because cross-linker is very expensive. We think about polyethylene tetrafosylate, PET, which is also a waste. It's something like a plastic waste, like the plastic of water we drink. If we make this plastic, do it like this with thermal treatment, we can further treat it thermally. You increase the heat up to 290, and then you make it cool it suddenly in water. Then you got some kind of foam like this. And then we got a functional group inside the foam. We found that this could remediate heavy metals, but we still have to study this because of PET has some limitation in many countries because of degradation, because of the bacteria, I don't know, but we can start to do this. If we have a microsphere like this, from this structure, it's much cheaper because you have water hyacinths with solar energy, and you got BET as a cross-linker. In this sense, you pay nothing. You got some waste, some agricultural waste, and some industrial waste. You put it together to have a sphere to remediate a third waste. So this is a class of how to manage waste from another waste, but it's just a playing. We were playing with quantum mechanics, and then we were playing with the waste in the laboratory. And the question is, does it work in the environment? We have to test, we have to be sure that it works or not. Okay. Also, if we're going to describe what happened for the pharmaceutical in the environment, the absorption of or complexation of ibuprofen, for example, in the surface of clay minerals, we have started to make some model molecules, and we cooperate with Dr. Paula. We hope to complete this in the near future. This is the future of cooperation between us and between Anna and Paula, and willing for question. And I'm really happy that I'm here once more, and I hope that this will be interesting to you.
Thank you, Professor Meda. Very interesting for many point of view, your research, and if you have some questions to Professor Meda,